insert this. I think I have a movie anyway, but I'll just put one in there anyway. Okay, so what we want to talk about is acids and bases. The thing about acids and bases is that you have talked about acids and bases in grade 9 and in grade 10. I don't know if you talk about acids and bases in elementary school. I've not encountered my children coming home indicating to me that they've had a discussion about acids and bases, so I don't think so. So you would have in grade 9. Do you do acids and bases in grade 9, the chemistry part? Do you just in grade 10? Just in grade 10? So in grade 10, hopefully your teacher would have talked about how you identify an acid. Maybe with litmus paper, you would have, put in the litmus paper, and if it turned red, what if the blue one turned red? What is it? It's a acid. Yeah, very good. And if the red one turns blue, it's a base. And you would have maybe used other indicators. You might have used phenolphthalein. I'm not sure. That's the magenta one and colorless. I don't know if you would have looked at that. If you got a really keen teacher, you might have taken some red cabbage and boiled it up and made some red cabbage juice, because that actually works as an indicator as well. It's a natural indicator. I remember years ago I did a lab where I must have been a young teacher in Keene. I took a whole bunch of petals from various flowers. I think it was at my mom's house. She was furious. So I pulled off all the petals from all these flowers. And if you take the petals and you boil it up in some ethanol, some alcohol, you can draw the color out of it, and that will actually act as a natural acid-base indicator as well. You may have talked about the pH scale. Did you last year talk about the pH scale? And you might have put various things on that pH scale. You might have done some testing with some pH paper. And so obviously the pH scale is a measurement of acids and bases. Excellent. We will be talking about all those things at some point in time. We'll be talking about indicators and where we use them. We'll be talking about the pH scale, except this time we're going to be actually doing calculations associated with the pH scale, because the concentration of the acid, and now that I was going to say know how to use concentrations, but let me change that. Now that I've taught you about concentrations, we're going to use that. Yeah, that was a shot, by the way. We're going to use that in order to determine pH, because pH is actually a measure of the concentration of the acid in the base. It's probably not a stretch for you to realize that if you've got a lot of acid in water, right? In other words, if the concentration is high of that acid, then your pH is going to be very, well, do you remember how does pH affect that? Is it high or low if it's a strong acid? The pH is going to be very low, right? So we're going to be able to actually calculate how concentrated it is, or if you know the concentration, what will the pH be? So we'll be able to do calculations on pH. And then ultimately we'll talk about neutralization reactions, and we will do some experiments with some specialized neutralization reactions. Today we want to talk about acid-base theories. So let's first talk about properties of acids, just those basic properties that I've just mentioned. And again, you would have wrote those down in grade 11 somewhere. So this is really just a review, a reminder of all those important things that deal with acids and bases. Acids taste sour. They change indicators of characteristic color. And I didn't mention litmus in this case, but we'll get that stuff written down eventually. But that's the litmus paper. Litmus itself is a chemical. It comes from a plant. And then when you soak the paper in the litmus, a solution of the litmus, then it takes on that color. It's got those chemicals kind of in the paper, and then we can use it as a useful thing. Same with if you use pH paper. It's simply indicators that have been soaked into that paper. And indicators have certain colors in acids and certain colors in bases. They're all electrolytes, all right? Remember, electrolytes means they will conduct electricity. So if you have an acid, you put it in water, you use a little conductivity tester, you will find that it conducts, and they have pH below 7. Nothing surprising there. And this is true for all acids. Don't write down this last thing. It just is a statement. If all acids behave the same way, then therefore acids must have a common feature in order for them to have the same characteristics and properties. All right? So there's something common about all acids which gives them this ability. Let's just write down some acids that you may have come across, and you actually can look up some of these in the back of the book. These are common chemicals, but let's just talk about some of them that you may have encountered personally, and we'll just maybe make a note of what they are and how they're acidic, or that type of thing. So the name of the acid, or perhaps you might know the common source, and then if I know the formula, we'll put it down. An acid that you may have encountered in your life. Yeah. Suggestions? Yep. Vinegar. Excellent. So that's the common source, right? So we've got our vinegar, right? And we've used this as examples in the past unit over and over again. What's the acid called? Yep. Yeah, very good. Acetic acid. Acetic acid. And its formula, CH3COOH. Another common property of acids is if you have a little cut in your finger and you get a little acid in there, oh, it stings like crazy. Yep. Yeah, very good. Citric acid. We'll put this here. Citric acid. I have no idea what the formula is. It's what we would call an organic acid. It means it's made up of a big molecule that contains carbons, hydrogens, and oxygens. And there is a feature of that molecule which is just like all the other acids, which I'll describe in a moment. But I don't know what that formula is. I've seen it in a textbook various places, but it's a pretty big molecule. I don't have it memorized. Sources of citric acid. Yep. Yeah, lemons, citrus, fruit, right? So lemons, right? Oranges. What did I do here? I wrecked it. Citrus. Or is it citrus? I'm losing it. Yep. Yeah, very good. Carbonic acid. Carbonic acid. Whew. I'm blowing it to pieces. And pop. Carbonated beverages, etc., etc. And that is, does anybody know the formula of carbonic acid? Well, this is one we should know. Yep. We're close. Look at the CO3, look at the charge on it. So what do we need? H2CO3. Excellent. Other acids that you might have encountered? Yep. Yeah, hydrochloric acid. Hydrochloric acid formula? Yeah, HCl. HCl. Where do you find hydrochloric acid? If you were looking for a common source of hydrochloric acid, no problem. Yep. Where would we find hydrochloric acid? Anybody know? Common source of hydrochloric acid, other than like in a laboratory, that like I gave you. No ideas? All right. If you were to go to a pool supply store, I know that when my father, he ran a little trucking company, he would haul pigs to market, and he had a pig trailer. You've seen them around, right? And they're made of aluminum, and he would sometimes clean the exterior of that trailer with a weak solution of hydrochloric acid, and it would take off all the dirt very nicely. If you were to go to a farm supply store or perhaps a pool supply store, you would see it as muriatic acid. All right? Pools have to have appropriate pHs in order for the other chemicals to work, to do their job, to clean the bacteria out from the water. And so sometimes you need to adjust that pH. And if you've got a large pool with lots of water, the easiest way is to add some muriatic acid. And what you're doing is you're essentially adding some hydrochloric acid. And that would bring the pH down. All right? Others? Yep. Phosphoric acid. Yep, phosphoric acid. Formula for phosphoric acid. Yep. Yeah, H3PO4. Now, are you just picking out some of the acids that I've named before, or do you know where phosphoric acid is used?
I'm just remembering one.
That's fine. That's good. Does anybody know where phosphoric acid is used? It's a very strong acid, can be a little dangerous. It's battery acid. Now, when I say battery acid, I'm talking about a lead storage battery, which is the battery that's in your car or in your boat, all right? I'm not talking about a little battery, okay? Those are completely different. But a battery in your car contains acid, and, you know, if you were to spill that on yourself, you want to get that cleaned off fairly quickly because it's a fairly strong acid. If you've worked with cars before, if you've ever noticed that sometimes, well, no, I better watch what I'm saying because that's a different effect. That's corrosion due to the electricity. Let's just leave it at that. If you've ever seen the little batteries, you know, let's say you had a toy when you were like 5, it was the greatest little electronic toy you've ever had, and then of course it ends up in the back of the closet, and you leave it there for who knows how many years, 10 years, and you find it's like, wow, this is great, I love this game. You start to play it, it doesn't work, you check the batteries, and those batteries are oozing white stuff. Ever see that before? Yes? No? All right. Now, little batteries are what we call alkaline batteries. Instead of using an acid to assist in making the electricity, it uses a base. Another word for base is alkaline. So that powder, that white stuff that you see, is basic. It's not acidic, all right? And it's not as strong as the phosphoric acid in a lead battery, in a big battery you have in your car. So it's not like if you get it on your skin, you know, your finger's going to ooze away and, you know, there's going to be a bone sitting there, right? Because so sometimes it's like, no, it's a battery acid. Be careful, you know what I mean? And you should be careful with it. It is a chemical, but it is not acid. It is actually a base. It's a different type of battery. Okay, any other acids? We've got a good list here. Yep. Well, now you're just picking them out, right? And it's a good job. That's good. Nitric acid, I don't know of an application where you see, I'm not going to write it down because I don't have a common application for it. And that's really what I want to discuss. He's going up and down the list. That's nice. That's a good job. But nitric acid is an industrial acid. Where would we encounter nitric acid in our everyday lives? I don't have an example of that. Nitric acid can be fairly strong. Nitric acid can break down and form nitrous oxides, various types of oxides. It's not used very often in just general things. All right, I think Brendan has exhausted his list. So let's keep going. Unless somebody has another one that they thought of and want to add. Actually, there is another one that I usually write down as you're writing this down. Ascorbic acid. You might have heard of ascorbic acid. And ascorbic acid is also known as vitamin C. So vitamin C itself is an acid. All right. Another one, salicylic acid. All right. Salicylic acid is aspirin. All right. And from the 1960s, if you've ever heard of acid, LSD, it actually technically is an acidic compound. That's why it's called acid. And if you were to dissolve some in water, it would decrease the pH. It would behave like an acid. So now we want to talk a little bit about what makes these things all acids. Now I've already described to you when you write the formula for an acid, it's going to start with an H. And it is this H that is very important in an acid doing its job. Arrhenius actually came up with the idea of dissociation and ionization. I actually read a little bit about this last night. I don't know how I came across it. As I stated, in the mid-1800s, scientists were using electricity to zap absolutely everything. And so scientists were creating solutions of things and putting electrodes in it with electricity and seeing what it would do. Michael Faraday believed that the electricity was actually ripping molecules apart. that it was the electricity that was pulling them apart. Now, when they said molecules back then, they meant every compound. They might not even have used the term molecules. I don't know when it was originated. But they believed that the electricity was pulling the compounds apart. Whether they were molecules or whether they were ionic, it didn't matter. Faraday believed that when you put sodium chloride in the water, the sodium chloride stayed together. It just dissolved. And then when you put the electricity, it was the electricity that pulled the sodium and the chlorine apart. That's incorrect. It was Arrhenius that, for various experimental reasons, said, no, I don't think it's the electricity that's pulling them apart. I think as soon as they hit the water, they're falling apart. Dissociation. He was correct. The ions dissociate upon dissolving. It was the electricity that caused them to move around and then go to the electrodes and do neat chemistry. So Arrhenius really came up with this idea of ionization and dissociation. That when something hits the water, it can fall apart. So he stated that acids are molecular compounds which ionize in water to produce H+. Ionization is the process where a neutral molecule forms ions when dissolved in water. Ionization is slightly different than dissociation. When something like sodium chloride hits the water, it's already in its ionic form. They're already traded their electrons and they've formed ions. When they hit the water, they just separate away from each other. So that's a dissociation. No need to create the ions. But when something like an acid hits the water, this is molecular, and something happens when it dissolves that results in this pair of electrons going to the chlorine, leaving an H+ without its electron, and leaving a Cl-. So because an acid starts as a molecule and is not in its ion form, when it hits the water, it becomes ions. We use the term ionized. Ions were created when this neutral molecule hit the water, and then the electron trade happened. It took it away, and we now have ions formed. For something like sodium chloride, which already exists as ions before it hits the water, when it hits the water and separates apart, we simply call it dissociation because the ions were always there to begin with. So one forms ions, ionization. The molecule then becomes ions when it hits the water. And the other one that we already seen, they're already ions. They just dissociate from each other. Okay, so there's a slight difference in that. Arrhenius, when he first came up with the idea, I think just called it ionization because they weren't thinking in that much detail. We now know there are slightly different processes. So ionization is the process where neutral molecules form ions when dissolved in water. It is the H+. So when this H+ falls off and gets into the water, it is the H+ that does all the things that acids do. And because all acids do this, and the H+ is liberated, then litmus turns red because of the H+. And acids taste sour because when we taste them, the H+'s interact with our taste buds in some way, and we taste sour. All right? Yep.
Obviously, all those things are used or whatever.
Yep.
Like, what if they were here today and they found out all this stuff we know?
What would they think? Would they be amazed and all that stuff? This is completely off topic. That's right. Good. You're derailing this pretty good. I actually hope to show a video later on, but hey, if you want to occupy that time with discussion, that's fine. What would they do? They would be in disbelief for a long time. Yeah, that's typically what happens to old scientists. When old scientists are presented with new information, old scientists tend to say, "What? You're telling me everything that I thought was wrong? I don't believe you." Right? And then it takes a long time for them to change their views. That's why scientific progress actually is limited by the lifetime of human beings because old scientists say, no way. And it isn't until they die that the new scientists can say, we were right. We're going to keep going now. Thanks for dying. So we can keep going. So they'd probably be in disbelief, would be my guess. Well, that's just it. Yeah. They need a lot of evidence. They've got to absorb that evidence, right? It's like anybody else. If you aren't convinced of a story that somebody tells you, then you're not going to believe it, right? Let's say somebody comes along and says, did you know what happened last weekend? My buddy, he did it. Oh, yeah. Oh, crazy. And you say, what? I don't believe you, right? If you don't believe it, you're not going to buy into it, right? And that's the way that kind of functions. Okay. So let's do some examples here of some ionization reactions. This is very much like equations that are for dissociation reactions. We actually do them exactly the same. The only difference is we're starting with molecules, all nonmetals, as opposed to starting with the metal and the nonmetal of the sodium chloride. So in this case, I've got an H and a Cl. It hits the water. The H plus falls off. H plus, aqueous, and Cl minus, aqueous. In this case here, we've got nitric acid. Again, the H plus falls off, aqueous, and then the NO3 minus, aqueous. And with acetic acid, it's also an organic acid, like the citric acid, except it's one of the smaller ones. You'll notice it's made up of all kinds of C's that are separated out and some O's. It's this NH is the one that falls off. So H plus, aqueous, and CH3, CO. I like to separate out the O's. I really don't like it this way, so I'm going to write it COO minus, and that's aqueous. Again, when you separate out the O's as a chemist, we see that COO. That tells us that that came from an organic acid. All right, if you didn't do that, it wouldn't be a big deal, but that's the representation there. Yep?
Ionization energy, we looked at earlier, have anything to do with ionization?
It is different. It is different. Ionization energy, remember, is the energy needed to take an electron away to form an ion. This is turning a molecule into ions. So it's forming ions. Would there be an energy associated with taking that H off? Yes, there would, but it wouldn't fall under what we would call, that I introduced you to at the beginning of the course, ionization energy. So there are different ways of forming ions, and so they have different definitions. There would be energy involved with this, because you're taking the positive away from a negative, but it's not what I defined to you as ionization energy. All right? It's a good question. Okay, let's talk about bases. So again, properties of bases, they taste bitter instead of sour. I don't know if you had a chance to put some base on your hand, but they do feel slippery and slimy. Some teachers, if it's a weak base, you put some on your hand, it feels slippery and slimy. They change indicators of characteristic color. They change red litmus blue. They are also electrolytes, which means they break into their ions, and they have a pH of above 7, and again, I think that is nothing groundbreaking. Don't have to write that down. Again, that just simply means that if all bases have this, particular set of properties. There must be something common about the bases that results in this. Let's just then do a quick little rundown on some common bases. Common bases that we may encounter in everyday life that you might know of. Any ideas? Yep. And you have no idea where we would encounter sodium hydroxide, but that's the first base that came to your mind. Excellent. That's good stuff. So let's write down sodium hydroxide. NaOH, and in some drain uncloggers. I don't even know how else to say that. Like Drano, you know what I'm talking about? You got a clogged drain, you dump some that in there. Now what happens is the sodium hydroxide, and there's very strong sodium hydroxide in that. Sodium hydroxide is mixed with aluminum at some point in time, which produces a large amount of hydrogen gas. That hydrogen gas expands in the clog and it moves everything, all right? Very strong sodium hydroxide. You spill some of that stuff, you want to get some of your baking powder and you want to sprinkle it on there. Normally I'm a pretty tough guy when it comes to cleaning up household chemicals, but if I were, and I haven't spilt any of this because I know it's dangerous, but if you were to spill the Drano, you do want to put some sodium bicarbonate on it. What's that? What do you mean what happened? Well, if you cleaned it up and you didn't put gloves on or you didn't neutralize it, you would burn your hand. You'd get a burn. You'd get a chemical burn, right? So that's what would happen. Yep. Yeah, that's a good observation. Many cleaners do get their slipperiness from the fact that they're bases. Many cleaners are bases. Laundry detergent, though, is a complex molecule, and I'm unsure if it's due to a base or not. It might be. I just might not know enough about laundry detergent to tell you conclusively that that's the case. But if you've used something like window cleaner, like Windex, or even something like Fantastic, you know what I'm talking about, Fantastic, that type of thing, and you get it on your hands, and then when you're done, you clean your hands, right, to get all that stuff off, you'll probably notice it's very slimy, and those are due to bases. Do you have a base you want to add, Chelsea? Because I have some that deal with cleaners that I could add, but what have you got? You put your hand up? Okay. Some of the stuff that's in those cleaners like Windex is ammonia, all right? So ammonia, NH3 is a base, all right? And things like I'm just going to put cleaners, cleaners, Windex, all that type of stuff, whatever type of cleaner or window cleaner you use. Other ones that can be in there, I'm trying to think. Ammonia and then ammonium hydroxide. It's a version of it. Ammonium hydroxide. NH4OH. Again, cleaners. That's all I got right now. What do you want to add there, Chelsea? Tums, very good. Tums is, it's a tricky one. Tums is calcium carbonate. CaCO3. And that is an antacid. Milk of magnesia, magnesium hydroxide. Magnesium hydroxide. I'm just going to write it down as that. Magnesium hydroxide. Again, we would call that milk of magnesia, right? That's used as an antacid as well. One that is a cleaner, but it's not, you don't use this to, say, clean a surface. You use it to disinfect a surface, and that's bleach. Bleach is a base. And that is sodium, I got it backwards, bleach. and that is sodium hypochlorite. Hypochlorite. Oh, I made a mess of that. Sodium hypochlorite, NaClO. Bleach is a base. You might think of it as a cleaner. It does whiten things because it'll react with certain pigments, but it also kills bacteria. It is the hypochlorite, the ClO minus, which is responsible for killing bacteria and things like that. Okay, there's a good list of bases. And as you guys are writing this, I'll get my test writers ready to go, so you guys can, well, and this is online, you'll be able to find it. You guys can close up, get your periodic tables and calculators, and I'll move you into the corner here. You can mark up the multiple choice, so you can just kind of doodle away on it as you're thinking. Yep. Are you checking that right now? Oh, all right. I'm just concerned. We had illegal use of devices. Yep. A couple of little corrections on there, but I made them for you. Here, let me just take a look here. There's a couple of little corrections that I found as mistakes. I'll just put the page here for you. So this is also hydrochloric. And this is potassium nitrate. Okay? All right. Good to go. Okay. So, Arrhenius definition of bases. Bases are ionic hydroxides which dissociate in water to produce OH minuses. Again, we've already encountered dissociation. Because they're ionic compounds to begin with, they don't need to ionize. Therefore, they just have to kind of fall apart. It is the OH which is responsible for all the characteristic properties of the bases. Oh, this symbol here, I haven't introduced it to you yet, but I should mention it to you. If you have square brackets around a chemical, it represents molar concentration. We'll see that again in the future. I'll write it down when we see it again. But when you have square brackets around a chemical, you're going to have to eventually learn that when you see that, it means it's molar concentration, moles per liter is concentration. So what this statement says is, the greater the molar concentration of OH, the more there is, the stronger the base. Now, I don't know if you noticed, we now already have a problem with the Arrhenius definition of a base, because on my previous slide, many of our base examples, you'll notice, don't contain hydroxides. Calcium carbonate in Tums does not contain a hydroxide. Sodium hypochlorite does not contain a hydroxide. So the Arrhenius definition was the first idea of what makes acids acids and what makes bases bases. But on Monday, I'm going to introduce you to another idea. It's called the Bronsted-Lowry theory, and it's a better theory to explain how acids and bases behave. Now, this is a good starting point for us because it still works on what you've been taught in the past. If you've got something that has H pluses, it's an acid, and if you've got something that has OH on it, it's a base, and that's still a good starting point. We will still be using these ideas, even though they don't fully cover our knowledge of acids and bases. They're a very good starting point, all right? So we don't want to just discount the Arrhenius theory. A little bit of practice in terms of dissociating to produce OHs. You go ahead and dissociate those. We're just breaking them apart into their ions. My little handout is still back here. Actually, only the first two questions deal with the Arrhenius theory. It'll be a good review on Monday. I will hang on to that and we'll hand that out on Monday. The rest of the questions deal with the next theory, so I'm going to save that. Okay. NaOH, Na plus aqueous, OH minus aqueous. MgOH2, Mg plus 2 aqueous, 2OH minus aqueous, right? Just like we were doing when we were doing our dissociation, right? And NH4OH, NH4 plus aqueous, OH minus aqueous. And these we would consider all Arrhenius bases because they all produce OHs. They all have OHs on the back end, all right? Some of our bases that we saw 2 slides ago, that wouldn't be a base according to Arrhenius. But it is a base when we stick litmus paper in it. It will turn litmus paper blue, and it will be slimy, and it will taste bitter. Don't taste bleach, please. That'd be dangerous. But if someone was really dumb and they tasted bleach, it would taste bitter. Anyway, so there is something more than this simplistic view. So according to Arrhenius, all of those would be bases. Okay? Let's just talk a little bit about what Arrhenius thinks as being a neutral solution. And then we're almost done, and then I'll show you a little video that reviews properties of acids and bases and uses of acids and bases and things like that. Hello.
Chris Johnson.
He's writing a test for me.
In the corner?
Yeah, he's in the corner.
I was watching a Goldfinger TV the other night.
Excellent.
Taking photos. His license plate, EU1.
Ah, very nice.
Not asking you. That's right. Then my 12-year-old son sees, hey,
Oh, that's funny. You haven't seen the video or the movie, have you? Have you ever seen Goldfinger? Yeah, he does look like Rob Ford. You got that? Okay. The Arrhenius definition of a neutral solution. So if it dissociates or ionizes, it does not produce H pluses or OHs. Sodium chloride breaks down, does not produce H pluses or OHs. According to Arrhenius, it would be neutral. Some neutral substances are non-electrolytes. We've already talked about this. Things like methanol, they will dissolve in water, but they won't break into their ions. They'll stay as molecules, kind of like sugar. And so they also will remain neutral because none of the H's and none of the OH's fall off. Okay, so at this point, I did have some more examples, but I think we are getting these. There's some homework in the bottom corner here. You can write that down. And for the rest of the class, we will watch a little movie that, like I said, goes over acid-base properties, etc., etc. And I'm going to stop the recording as you're writing that.